Okay, so this is some guiding comments to assist you into 7E and 7G while I'm not with you on Wednesday. So 7E is about using trigonometric identities for integration. And the three cases we're going to look at when we have the products of sines and coses, that is sine to the power of m of x times cos to the power of n of x. Case A is when the sine is odd, that is m is an odd number, or the power on cosine is odd, that's case B, and then case C, where both powers are even. Some examples. Now remember, these are the trigonometric identities that we're going to play around with, the double angle formulas for sine and for cos. Remember, I can rewrite the cos squared x minus sine squared x just in terms of sine or just in terms of cos. Just in terms of sine can be rewritten as this in terms of sine squared of x. And cos squared of x, I can use this to replace it. I've also got this rule, which comes from my cos squared of x plus sine squared of x equaling 1. And we have sec squared equals 1 plus tan squared. Okay, case A. When my sec to the power of 3, what I'd like to do is I'd like to rewrite that as the integral of sine squared of x times the sine of x dx. And with my sine, change that to 1 minus cos squared of x sine of x dx. So when I multiply that out, I end up with two integrals, the integral of sine of x dx minus the integral of cos squared of x sine of x dx. This one is antidifferentiable. This one, if I make u equal to the cos of x, du dx equals the negative sine of x, and I can use the sine of x dx to do a replacement. What does that look like? It looks like this. So my sine cubed became sine squared times sine. I replaced my sine squared with this, therefore these two, and end up with two separate integrals, and that ends up being my answer. When the cos is odd, I'm going to rewrite that as the cos of x to the power of 4 times cos of x dx. Then I'd like to consider this as being the cos squared x squared, cos of x dx. And what that looks like is this. So my cos of x becomes to the 4, that becomes cos squared squared. I've replaced my cos squared with minus sine squared, expand. Therefore, I can use a substitution for u for the sine of x, and also u for the sine of x. And this is what the integration looks like. I'll leave that for you to have a look at. And where they're both even, I'll let you have a look. So what have we got? I'm going to be turning my sine squared cos squared into sine becomes 1 minus cos squared, multiply that out. That gives me a cos squared minus a cos to the power of 4. Cos squared, I'm going to use the double angle formula to do a replacement of cos squared. And cos to the power of 4, I'm going to do like I did in the last example, cos squared squared. The cos equals this using the double angle formula. Expand it all out, which gives me this expression. I can put that back there, combine it, and my end product looks like this. I'll leave that for you to have a little look at. So here's an example of sine x to the power of 4. I'm going to replace my sine x to the power of 4 as sine squared squared, and do the substitution using the double angle formula for cos of 2x in terms of sine squared. And as you can see, that's where it goes. Again, I'll let you have a little look. For my sec squared of 2x, I know that the derivative of tan is sec squared. Therefore, the integral of sec squared is tan of x. So since I've got sec squared of 2x, I need a 2, so I can balance it out the front with a half. It's going to be a half tan of 2x. And the same thing, but with terminals. I'll let you work through and look at those examples yourself. 7f is not in our course. When we're looking at partial fractions for 7g, we cannot take the antiderivative of this, so we turn it into partial fractions instead. I can turn my improper fractions into proper fractions by doing a polynomial division. And there is my polynomial division, which turns it into this. I can integrate this. I can integrate this, but I can't integrate this. So I need to turn this into partial fractions by working out what a and b are. So you then end up with 3 terms that can be each integrated separately. When we have distinct linear factors, that is 2x minus 3 and x plus 5, I can write them as 2 separate fractions. When we have a repeated linear, I need the 2x minus 3, the x plus 5 and the x plus 5 squared, and they're all constants on top. And where we have an irreducible quadratic, that is the x squared plus 5 can't be factorised, I put that as bx plus c. So to decompose this, I would be writing this as being 9 on those two as being x minus 10, x minus 1 equals a on top of x minus 10 plus b on top of x minus 1. Therefore, a times x minus a times 1 plus b times x minus 10 times b all equals 9. So I've got a plus bx minus a minus 10b gives me two equations. Since there's no x's over here, a plus b equals 0, and minus a minus 10b equals 9. And then that looks like this. I can solve for b and a. I can write it as 2 separate fractions. Then I can integrate them separately, which gives me logarithms. To decompose this, then I'd be saying 7x plus 1 over x plus 2 squared would equal a on top of x plus 2 plus bx plus c on top of b on top of x plus 2 squared. And then that would look like this. Solving that gives me my two values for a and for b. Putting it together as 2 separate fractions, I can then use a logarithm to integrate this one and use the x plus 2 to the negative 2 general rule to do them separately. Looking at question 7g, I would need to do a polynomial division first. And once I do a polynomial division, I then end up with this. With this, I need to do partial fractions of the x squared plus 1 over x squared minus 4, which gives me this equals these terms. This becomes an x squared on 2, that becomes minus 2x, that becomes a logarithm, and that becomes a logarithm. So today's work is partial fraction work and use of trigonometric identities.